Hi everyone, Jonathan here. In this video, I'm going to be giving you my take on section 5.5, which is about the substitution rule. So the substitution rule boils down to the fact that the integral of a function f applied to another function g times the derivative of g is the same as the integral of just f of u du if you let u be g of x. And they give a lovely justification of it here, which I assume you can read and understand on your own time. But the key takeaway from this is not that useful in its current form, because how often are going to be like, oh yeah, that's totally f composed with g times g prime. Instead, what you do is use this to allow you to choose some function to be u, and then to treat du dx, which remember is just notation for derivative, but the top and bottom we're going to treat as different variables. And using that, you can replace the dx with du, and you can replace x's with u's and get a new integral. I've written out explicit steps you can take in order to do integration by substitution, but be warned, unlike with anything you ever do with differentiation, there are choices to make here, and it is entirely possible you're going to make a choice that doesn't work out great and have to start over again. So the goal is to find the integral of some function or some expression, and the first step is to choose u. So in this example, we're going to try to find the integral of x divided by the square root of 3x squared plus 1. Now there's a lot of sub-expressions in this that you could let u be. For example, you could be x squared or 3x squared or 3x squared plus 1 or several other things. For reasons I'll explain in a little bit, what you want to let u be here is 3x squared plus 1. Now, after you've done step 1 and chosen u, the next step is to calculate du dx. Now, in this example, we let u equal 3x squared plus 1, and hopefully you all remember how to differentiate that. The derivative of 3x squared plus 1 is just 6x. So that makes our du dx equal to 6x. In step 3, you want to get rid of the dx. How do you do that? Well, in step 2, you calculated du dx. Now, this actually isn't a fraction, it's just notation for the derivative. However, the point of integration by substitution is you are allowed to treat this as if it were a fraction and dx is a variable. And therefore, you're going to have some expression with dx in it, some equation really, and you'll be able to find a way to replace the dx. For example, you can solve the equation for dx, and you replace this dx here in the integral of f of x dx. Now back to the example we were working on, we calculated du dx equals 6x. If I pretend that dx is a variable, I can solve this equation for dx and get dx is equal to du over 6x. Now I can go back to the original integral, take this dx and sub it out for what we found dx to be equal, which was du over 6x, and we get the integral of x over the square root of u times du over 6x. For step 4, you want to get rid of any remaining x's. Having substituted out the dx, there'll often be some x's left over. If you've chosen u well, a lot of times the remaining x's will just cancel at this point. Even if they don't cancel, sometimes you can find other ways to get rid of them. In our example, after we substituted out the dx, we wound up with the integral of x over the square root of u times du over 6x. And hopefully you all realize that having x in the numerator and x in the denominator allows us just to cancel them. Once those two x's cancel, there are no x's left over, and we wind up with 1/6 times the integral of 1 over the square root of u du. If all is going according to plan, for step 5, you've gotten rid of all the x's and dx's, and you have an integral solely in terms of u and du. So now, if you've chosen u correctly, this integral should be something you can figure out. So you find this integral using all the techniques you know. In our example, we wound up with 1/6 times the integral of 1 over the square root of u du. Well, I happen to remember that the integral of 1 over the square root of u is just 2 times the square root of u plus c, and then the 2 and the 6 and the 1/6 will cancel to 1/3, so we get the integral to be 1/3 the square root of u plus c. Now the final step is to substitute out any u's. The original problem doesn't have any u's in it, so therefore your final answer shouldn't have any u's in it either. However, you chose u to be some function of x, so all you have to do is replace every u with that function, and you'll have your final answer. In our example, u was equal to 3x squared plus 1, so I simply replace the u with the 3x squared plus 1 and get our final answer to be 1/3 times the square root of 3x squared plus 1, and of course don't forget the plus c. Students often find this hard because there are choices to make, and some choices will be better than others, and not every choice is going to work. So in step 1, I have you make a choice for u. So if it doesn't work, don't be discouraged. Instead, go back and try another choice for u. Furthermore, in a lot of problems, once you build up some intuition, choosing u won't be that hard. For example, try to choose u such that du dx shows up in the integrand, at least up to a constant. In the example we just did, possible choices for u were u equals x squared, or u equals 3x squared, or u equals 3x squared plus 1, or some of these other more complicated things. For these first three choices, however, du dx for all of them is some constant times x, and as you can see, x shows up. So the derivative of u is showing up, and that's a big hint that your choice for u is the right one. There will be problems where you won't be able to choose u such that du dx shows up, and even when du dx is showing up, it's often a good idea to try and let u be inside of something, inside of some more complicated expression. In our example, inside this square root in the denominator is 3x squared plus 1, and that suggests that letting u equal 3x squared plus 1 is the best choice. Now step 3 is to treat du dx as variables and find a way to substitute out the dx in the integrand. Now, as you get good at this, you can find efficient ways to do that, but while you're still getting up to speed, you can always do this by taking du dx equaling whatever it equals and solving that equation for dx. So when I teach this to students for the first time, that is what I have them always do. Since you've already read the book, you'll notice that sometimes the author of the book does this, but sometimes he finds more efficient ways to get rid of the dx. Now step 4 was to cancel or substitute out any remaining x's once you've gotten rid of the dx. It might not always be possible. In fact, if you just choose u carelessly or you choose the wrong re, it's usually not going to be possible. But that's okay. It's just telling you that you didn't make the right choice. So don't be discouraged. Instead, go back and start over with a different choice of u. The other thing that can happen is that when you get to step 5, you have to find this integral of some new function of u du. However, not all integrals can be found, and not all integrals, even if they can be found by an expert, they may not be able to be found by a beginning calculus student. So if you can't find the integral in step 5, then go ahead and start the process over with a different choice of u, and hope that when you go through the process a second or third or fourth time, you wind up getting an integral you know how to do. Now we're going to try a more complicated example. It's very similar to the last problem, but now we've got the integral of x over the square root of 3x plus 1. So there's a lot of possible choices you might make for u here. U could be 3x, u could be 3x plus 1, u could be the square root of 3x plus 1, u could be 1 over the square root of 3x plus 1, u could be x over the square root of 3x plus 1. However, if you go through each of those choices, and you take du dx and you solve it for dx, you're not going to be able to cancel this x up here in the numerator. It's not just going to cancel out of the way. However, that doesn't mean substitution is impossible, because sometimes you can find another way to get rid of any remaining x's. So in this case, what we're going to do is we're going to let u equal 3x plus 1. Why? Because 3x plus 1 is what is inside of something. In this case, it's inside of this square root. Going through the process, we've got du dx is 3, since u is 3x plus 1. Solving that equation for dx gives dx is du over 3. And then taking our original integral and replacing dx with du over 3 gives the integral of x over the square root of u times du over 3. So what to do with that remaining x? How can we get rid of it? A lot of times you're going to be able to go back to the original equation. U here is 3x plus 1. That equation can be solved for x. If you subtract 1 from both sides and then divide by 3, you get x equals u minus 1 over 3. So I can take this x and replace it with u minus 1 over 3. That's going to wind up with the integral of 1/9 times the integral of u minus 1 over the square root of u. And then if you split this up into two fractions and simplify, we get 1/9 times the integral of square root of u minus 1 over the square root of du, which is 1/9 times the quantity of 2/3 u to the 3/2 minus 2 times the square root of u plus c. And finally, we just replace the u with what it equals, which is 3x plus 1. And meanwhile, we'll simplify the constants a little bit and get our final answer to be 2 over 27 times the quantity of 3x plus 1 to the 3/2 minus 2/9 times the square root of 3x plus 1 plus c.